Hello everyone, welcome to this segment where we will be solving past paper questions regarding lattice energy. And to be honest, this is a very important part of the topic because CIE is all about past paper questions. Like trust me, if you understand the whole topic, you have read the notes, you know the theory, and you don't practice questions, it's very tough. So I recommend even if you don't have time to understand the lecture notes, but at least watch the past paper videos. These are things which will be very useful for your exam. You will know what the marking scheme expects answers to be in, and yeah, you'll basically know how to answer these type of questions. And also good things about CIE is that most of the questions have similar patterns. Like they don't change much from what the core concept is. So if you understand how to master these past paper questions, it's going to really help you to solve your CIEs. Right, so let's get started with the first one. This paper is from 2024 major, and the first question is define enthalpy change of solution. Now we have done this already, right? The definitions. So we say that enthalpy change of solution is the energy change or the enthalpy change when when 1 mole of a solid dissolves in excess water to form an infinitely dilute solution. So yeah, this is just a 1 mark question, and this shall be enough for you to get the mark. Right? So just straightforward. It's just enthalpy change when 1 mole of a solid dissolves in excess water to form an infinite dilute solution. We've already explained this concept of infinite dilute solution in the lecture. Right? Okay, let's continue. Now, the next thing here is that we are given some energy changes for silver nitrate as shown in table 4.1. So we have been given a few things here. The first thing that we've been given is the enthalpy change of solution, then hydration of silver ions and hydration of nitrate ions. Remember, this AgNO3 contains two different ions, right? There is Ag and there is NO3. So both of them have different enthalpies for hydration. And remember what we said about hydration. Hydration is basically going from gas to aqueous. So you will have maybe Ag plus gas forming Ag plus aqueous, right? And the same for NO3. And both of them have different energy changes. So that's why there's two different enthalpy changes over here. And this is enthalpy change of solution, right? So AgNO3 becoming, so we have AgN3 solid becoming Ag, Ag plus aqueous plus NO3 minus aqueous. Right, now what do they want? Complete the energy cycle in figure 4.1 to show the relationships between the lattice energy and the energy changes shown in table 4.1. So we have to complete this energy cycle. Remember this is it's a Bohr-Haber cycle, right? Which is an energy level diagram. But this time it's kind of different. They have switched the elements around. So what we have to do is that we have to interlink lattice energy with these energy changes, right? So basically we just have to fill in the blanks, like what is this, what is this, what is this, and how do the arrows go? Do they go up? Do they go down? From here to here, do they go up? Do they go down? And stuff like that. You have been given the arrow from here to here is down, and here to here is down. Remember what's the significance of this arrow? This arrow shows that if it's exothermic or if it's endothermic. If something is going down like this, it means it's exothermic. If something is going up, that means that it's endothermic, right? So now we have to fill in these. So we have to fill in solution, we have to fill in hydration, and we have to fill in another hydration. Now remember what we said about hydration in the lecture. We said that hydration is always exothermic. So this is exo and this is exo, right? And we also say that lattice energy is always exothermic. And the solution over here in our case, we said solution can be exothermic or endothermic. In our case, they have given us as endothermic. So you'll have how many arrows here? You'll have 4 arrows. 1, 2, 3, 4. And 3 of them will be exothermic and 1 of them will be endothermic, right? Now the problem here is that You see, we have these two arrows here going down, and we have to fill in these hydration values. So Ag is made from what? Ag has Ag plus and NO3 minus. So what you can do is you can keep this over here. Ag plus NO3 minus. Now remember, these two arrows are exothermic, so most likely this is hydration. So you have to keep gas here and you have to keep gas here. You can see that this one is going down, right? So this Ag plus gas is becoming Ag aqueous, or NO3 minus gas is becoming NO3 minus aqueous, right? So you can go with either of them. Let's say I take this one. So this is Ag plus aqueous plus NO3 minus still gas, right? Because this is just the hydration of Ag plus. Then we can do the hydration of NO3 minus. So it becomes Ag plus aqueous plus NO3 minus aqueous. So we are done with two of these, the exo. There's one more exothermic reaction over here, which is the lattice energy. Now, where is the lattice energy reaction? Remember, lattice energy happens when two gaseous ions combine to form the ionic compound. So you can see from here to here, this is lattice energy, right? So this will be the lattice energy. Now we still have one more error to go, which is the endothermic one, which is the enthalpy change of solution. Now, what is solution? Solution is when this solid breaks down to become two aqueous ions, right? So it's going from here to here, and it's going up with its endothermic. So this will be the enthalpy change of solution. So that's how you draw the energy cycle for this question. Now to continue, let's calculate the lattice energy for AgNO3. So what are we finding? We are finding this lattice energy, right? We are finding to go from here to here. Now, as always in Born-Haber cycles, to go from here to here, you can also go from here to here. You can go the longer edge, right? So here we can make an equation. We can say that the lattice energy is equal to, so we can start from here to here, plus from here to here, minus. Now you see, this arrow was going up, right? But we want to go here. This is where we want to go. So we will take the negative of this value so that we can go down, right? So we'll take the first value will be the hydration of Ag to Ag plus, which is negative 475. So you write negative 475 here, and then plus the next one is the hydration of NO3 minus gas to NO3 minus aqueous, which was negative 314. Now the next one, when I try to plus it here, because this is going up, the up one was positive 22, but we are going down, so we will keep a negative here, negative 22. And yeah, when you do the math here, is you'll get the answer as negative 811.6. Right? Let's go to the next one. So this is the trend in the magnitude of lattice energies of the metal nitrates NaNO3, MgNO3, and RbNO3. Right. So first, if you want to know the trend in the lattice energies, what are the things which affect lattice energy? If you recall from the lecture, that lattice energy is affected by two things. The first one is the size or the radius. Another one is the charge. Okay, so here let's look at the charge. The charge of sodium is positive 1, NO3 is negative 1, Mg is positive 2, NO3 is the same. Rb is in group 1, right? It's positive 1. So first of all, magnesium has positive 2, and these two have positive 1. So automatically, magnesium is more, like the lattice energy of magnesium will be more because of the charge, right? So you can keep the most exothermic part as Mg just because it has a higher charge. Now when you come to sodium and this rubidium, sodium is smaller because sodium is on top of group 1 and rubidium is down group 1. So sodium is smaller and rubidium is bigger. So you have rubidium and this NO3, and you have sodium and the NO3. Do you recall this pattern? This is the charge density stuff. Here sodium is smaller, so the positive 1 charge has a greater charge density. So that means that this one will be more exothermic because of the greater charge density, while the one in rubidium has a lower charge density. So the sodium one will be more exothermic because the more the charge density, the more the lattice energy, right? So here we will keep sodium Na3, and for the least exothermic, it's going to be Rb and O3. And regarding the reasons as to why that's the case, is that here you'll first say that magnesium has greater charge than sodium and rubidium. Then you should say that sodium Na plus is a smaller ion than rubidium, right? And therefore, stronger attraction ions, between ions, and hence greater lattice energy. You can also add a charge density over here. So Na plus has a higher charge density, so Na plus has greater charge density, right? That's it for question one. Right, let's go to the next question. Now, this one says that complete table 8.1 by placing one tick in each row to indicate the sign of each type of energy change under standard conditions. Right, let's start. Lattice energy, we just did this, right? It is always negative. Enthalpy change of hydration, we just did it above, it's always negative. And we also say that solution can either be positive or negative, right? So yeah, I hope this is clear and I'm doing it fast. Then define enthalpy change of hydration. So for definitions, I won't be explaining because these are basic things and we are just supposed to remember these definitions. So yeah, I've written for you the definition and yeah, you can read that and understand it. Table 8.2 shows various energy changes which can be used in the following questions. So we have a ton of energy changes over here. We have the enthalpy change of atomization, ionization, enthalpy change of atomization again, the bond energy, enthalpy change of solution formation hydration, and electron affinities. Select and use relevant data to calculate the lattice energy of CaBr2. It may be helpful to draw a labeled energy cycle and show your work. Right, so we'll start to draw our Born-Haber cycles. If you guys remember, when we are drawing the Born-Haber cycle, usually over here down, the first thing that we keep, so we have CaBr2, right? CaBr2 as a solid. What? Oh. CaBr2 as a solid is made from calcium plus bromine, right? Calcium solid plus bromine. Now, the first thing here that we'll keep is the reactants of where it's made from. Usually in Born-Haber cycles, we start with the elements which make up this thing. So calcium bromide, so this is Ca solid plus Br2 is liquid. Okay, because bromine is liquid under standard conditions. So this will be our thing over here down, right? And then we'll slowly start to make the sketch. If you need a recap of this, you can quickly check the lectures above and you will have a better understanding of why I'm doing this. Now, the next step will be to, because we want the lattice energy, right? We want the lattice energy. So we have to make the gaseous ions of these things. So this calcium solid has to become the gaseous ion, which is Ca2 plus gas, and this bromine has to become the Br minus gas, because that's how we form the lattice energy. We need the gaseous ions of these things. So again, we have to convert this to this. So the solid has to become a gas, and it has to lose 2 electrons. And to do that, we will do it step by step. We will start by atomizing the calcium. So, for example, here we can start like this. This calcium can become calcium gas plus Br2 liquid, it just remains. And this will be the enthalpy change of atomization. Then we can keep on going. And now this will be the first ionization energy of calcium because we want to remove 2 electrons from it. Plus Br2 liquid, and this will be the first ionization energy. Then we have to have another ionization energy as well. So we'll have another arrow which will have Ca2 plus gas plus Br2 liquid, and this will be the second ionization energy for calcium. So we have made Ca2 plus gas, but now this time we have to make Br2 into the gaseous ion. Let me just make space for this first. So now we'll continue with the bromine, and we'll have to make this Br2 liquid into bromine gaseous ions. So again, we'll do atomization of this. This will become Ca2 plus gas. It just remains like that. And this will become 2Br gas. Does it make sense? This is enthalpy change of atomization. But there's a bit of a tricky part here. First of all, atomization is for one bromine. So if you have Br2 as a liquid and you want to form Br gas, usually we do half of this, right? And then this will be the atomization. But this time, this is 2Br. So there's 2 here. So they've multiplied it by 2. So this is 2 times enthalpy change of atomization. Another tricky part is that we have the bond energy in the table here. So you see you have a BR bond energy which is 192.9. So some of you might be thinking that, so why don't we use this one? And why did we use this one? So why don't we just do BR2 forms 2Br? Because we have the bond energy. You are just breaking the bonds, right? You are just break the bond and you'll form these two atoms. Now the issue is with bond energy, this initial reactant must be in gas or else it doesn't work. Okay, so here our initial reactant is in liquid and it's not in gas. So this is very confusing to some people, but bond energy always works when you have gas as a reactant. So that's why we can't use bond energy over here. Like, CIE, they are trying every way to make you fail. But that's how it is basically. So if you have a liquid and you want to go into gas, you use atomization. Right? But if you had a gas here as a reactant, then you will use the normal bond energy. Right, so let's continue. Now here we have this one. Now we have to form the bromine ion, so we have to add an electron to it. And this will be the first electron affinity. So this will be Ca2 plus gas plus 2Br minus gas. See, there's two of them. So you will have Br minus times 2. So the first electron affinity of bromine times 2. Okay, is what we will form over here. Now lastly, this gas has to go into the main solid, which will be CaBr2 as a solid. I don't have much space here, but this is what it will form, CaBr2 as a solid. This will be your final thing, and this will be your lattice energy. And this will be the overall reaction. And what reaction is this? This is formation, right? Because you are forming the ionic compounds from its elements under standard conditions. So there you go. That's your Born-Haber cycle and how you will draw it. And to calculate the lattice energy now, you have to make an equation for this. So this is the overall reaction. So formation is equal to basically all this atomization of calcium plus first ionization energy of calcium plus second plus atomization of bromium, but this one of bromine, sorry, but this one will be times 2. And here this will be first Ea times 2, and this will be plus enthalpy change of lattice. So I'm calling all this from here until here. Let's just call it delta H from here to here. So this will be delta H plus enthalpy change of lattice. And yeah, you have all the values given here. So I'll be doing the calculations, but at the end you should get the answer of negative 2170.6. So this is what you will get. Let's go to the next question. Select and use relevant data from the table and your answer to theorem 1 to calculate the enthalpy change of hydration of Br minus. It may be helpful to draw a labeled energy cycle. Right, so what we can do is that the first thing that you have to identify is that you are given the hydration of calcium. Okay, you have the enthalpy change of hydration of calcium, and you want the hydration of Br, Br minus. Now, the way to solve this question is that you see here they say that select and use relevant data and your answer to serum 1. So you just get the hint that you will have to use the lattice energy that you found out in serum 1. So you know that there is some sort of use of lattice energy and some use of the data from table 8.2. Most likely this will be the hydration of calcium. So what we can do is that we can draw a Hess cycle equation for this. So basically, you can have this calcium 2 plus as a gas plus 2Br minus gas. So I'm just writing out the equation for the enthalpy change of lattice forms calcium Br2 as solid. But we can have some sort of intermediate over here so that we can get the hydration. So hydration is what? Hydration means the gas is becoming aqueous. So we can keep some arrow over here going down to show that calcium 2 plus aqueous plus 2 Br minus aqueous, right? And this arrow here will be a combination of the hydration of calcium plus the hydration of the bromide ion. Then to complete the cycle, this one uh, the solution can also go down over here. So this will be the enthalpy change of solution because you're going from the solid to aqueous, right? So this is lattice, this is solution, and this is the hydration. And we are given the values. So what we have to do is we have to find the specific one for this one. So let's make an equation first. You see this vector arrow is going here, head, tail, head. So we can do lattice plus solution equals to hydration, right? Enthalpy change of lattice, we have it above. It's negative 2170.6. So this one plus the enthalpy change of solution is also given, and we have it as negative 103.1. So plus negative 103.1 equals to, now hydration is I told you it's a combination of this and of this, right? Because there's hydration of this specific and this specific. So this one is given. It's negative 1579, negative 1579 plus the enthalpy change of hydration of the bromide ion will be 2 times certain value, let's say x, because that's what we are finding. We are finding this from here to here. This specific Br minus gas to Br minus aqueous, but there is 2 of them, so this will be plus 2x, right? And then you just do the math, and you should get your answer as negative 347, right? So this will be your final answer. Okay, the last part of this question now says that the enthalpy change of hydration of Br is more negative than the enthalpy change of hydration of the I minus ion. Now explain why. So first thing is that hydration is what? Essentially hydration is the attraction between the ions and the water molecules. Right? So between bromine and iodine, both of them are in group 7, so they have the same charge. This is negative 1 and this is negative 1 as well. But what's the difference between these two? I minus is larger than bromine. So this is the bromide minus and this is the I minus. And something which is smaller, remember the charge density stuff, has more attraction to other ions. So the reason why it's more negative or more exothermic is that bromine is a smaller ion than I minus. So that's exactly what you write. So Br minus has a smaller radius than I minus. That will be your first mark. And the second mark will be that therefore stronger attraction to the water molecules. To water molecules. Yeah, that's it for this question.